So in this video, we are going to investigate the circle theorem that a tangent to a circle is perpendicular to the radius drawn to the point of contact. So you can see from this picture that I have drawn a circle and a line next to it with a tangent at P here. So it's touching it at one point, and we're trying to prove that this is perpendicular, that the tangent meets the radius at 90 degrees. Now, in this video, we're going to do this via a proof by contradiction. It won't be as formal because I want to kind of build the intuition with you guys for how to identify proof by contradiction, or that something doesn't line up. But basically, we're going to make a statement and we're going to follow all the logical reasoning. And eventually we're going to see that some things just don't really add up. And that's going to lead us to a contradiction. Now, in the next video, I'll go through this a lot more formally, but just bear with me now as we sort of introduce this idea. Now, we're told that we have a tangent that basically touches at the point T. So our line ST, it touches the circle at P. And we're trying to prove that these are perpendicular. So how contradiction works is we're going to suppose that OP is not perpendicular to ST. Okay, so obviously you guys are looking at this and you can pretty clearly see, oh, well, that looks like 90 degrees. Like, why are we even doing this? But we need to go through this kind of logical, rigorous kind of process in order to make this proof. So we're going to just suppose that OP is actually not perpendicular to ST. But what this means is that there must be some point along this line where it will be 90 degrees, that it will be, this tangent line will be perpendicular to the radius. So what we're going to do is we're going to take this point Q on our line, and this passes through point R, which I've drawn in, which lies on our so the circumference of our circle. And we're going to say that therefore, because we're supposing that OP is not perpendicular to ST, there exists a point, let's call it R, as I put in here, such that, exists a point Q such that OQ is perpendicular to ST. Okay, so we're going to now assume and say that there exists a point Q, which I've drawn in, such that OQ is perpendicular to ST. Now, I know you're looking at it, you're going, well, this looks like an acute angle. I know it's not, but just try to visualize it. We're trying to make a contradiction here. We're trying to follow the logical steps. Now, since we're saying this is perpendicular, then the angle OQP equals 90 degrees. Okay, so this must equal to 90 degrees. Now, what we've basically drawn is, you can see with OQ and P, we've drawn a triangle. Now, because it's perpendicular, this is a right angle triangle, okay? So this one here must be a right angle triangle. So in a right angle triangle, if you remember, let me just draw one up. If you consider your right angle triangle, the biggest angle in your right angle triangle is 90 degrees, okay? So because it's 90 degrees, the angle sum of a triangle is 180. So each of these two angles here must be less than 90 degrees. The 90 degrees, the right angle, is the biggest angle on a right angle triangle. So with this in mind, we're going to say because OQP is 90 degrees by our statement, therefore, we can say that angle OPQ is less than angle OQP. That's from that example that we talked about. So if we're making this angle here 90 degrees, this angle must be less than it. Now, let's just think back to what we know about geometry when it relates to triangles. Now, if I draw up a triangle, right? Something to remember about triangles is that the longest side here corresponds to the largest angle. The shortest side corresponds to the shortest angle, okay? So something to keep in mind here, it's a basic thing with triangles, but we remember that as you draw that angle as bigger, so let's just draw a really big angle, the side opposite it is the longest side. We can clearly see here, it's the longest side. Sorry for the bad drawing, but you get the idea. So with that in mind, we're going to go back to our picture and we're going to make a little observation. Now, if this angle is the biggest angle, then the side OP must be the longest side because it's the side opposite my right angle, right? This in theory would be the hypotenuse. So we can say, therefore, OP must be the longest side. But if we look at this picture, we can clearly see OP is the radius of the circle. OQ is the radius of the circle, hitting at this point R, and then some. So something's not adding up, right? A contradiction exists. Therefore, our statement, we've supposed that it's OP isn't perpendicular to ST, and we've now assumed OQ is perpendicular to ST. This all goes out of the window because there is a contradiction. If in fact there was another point that wasn't at the point P where it was perpendicular, then the side OP opposite this angle should be the longest side, but it's not. OP is the radius, OQ is the radius and then some. This means that there's another angle that must contain that right angle. Now, I know we haven't formalized it in proof, but now that we see OP must be the longest side, but it isn't the longest side. Isn't the longest side. Therefore, a contradiction exists. So, there's a problem, right? Now, I'm going to show you in the next video how we're going to formalize this, but this is just to give you a bit of an intuition into how proof by contradiction will work as it relates to our particular circle theorem we are investigating here. But hopefully this gives you a bit of an idea of how this will work. We'll formalize this more in the next video. But now that we have a contradiction, we cannot go with this claim over here. But we'll get to more of that in the next video. Thanks so much for watching me, and I'll see you then.